Good. Our first session this morning, we have the ESR2 and go. We talk about effect algorithm for polynomial optimization.
Thank you for the introduction. So today I'll be presenting the works of my PhD thesis, which contains joint works with Ellen Bostan, Hugo, Giorgio Ottaviani, and Ettore Turati, as well as, of course, my advisors, Jeremy Bertemu and Marv Safialdin. So my PhD is entitled Exact Algorithms for Polynomial Optimization, and I'll just begin by breaking down those two parts. So firstly, of course, polynomial optimization. The primary goal is to compute an infimum of a polynomial over some semi-algebraic set. So that's some set defined by some polynomial equalities and inequalities. But I note that in this talk, all of the results you see are just for algebraic sets. So we're only considering equalities. Then the second half of the title, so an exact algorithm, is one that returns a non-zero polynomial where the infimum is a root of that polynomial. And so we can find it to whatever precision we require using a real root finding algorithm. This has several advantages and is required for many different things. So firstly, as we've heard a lot about today, there's the issue of certification. So this avoids any potential false infimums that can occur using numerical methods. There's also an issue of efficiency. So for certain problems, exact methods can actually be faster than using numerical methods, and that's either just by applying them directly or by using them as a kind of preconditioner to speed up the semi-definite programming. And there's also universality. So the methods I'll describe in this talk can be generalized to solve many different problems, including those that depend on parameters. And they can also tackle problems with fewer assumptions. So in particular, going to be focusing on non-compactness. So as we know in the compact setting, the Lagrange multiplier theorem tells us that polynomial optimization boils down to computing critical values and critical points, which are the minima and minimizers respectively. So if we take this example of just the projection map restricted to a circle, we can just compute the critical points and then project them onto the critical values. But if we take a non-compact example, such as this global optimization problem, then we see that although this polynomial f has a critical value at 1, if we take a path where x1 goes to 0 and x2 goes to infinity, like 1 over x1, then f tends to 0. And this is the infimum of the polynomial since it's a sum of squares. And in this case, we call it an asymptotic critical value. And together with the critical values, they make the generalized critical values, which is what you need to handle the non-compact case. So why does this work? It's mainly due to these theorems by Kottke and Unek. So firstly, they showed that the set of asymptotic critical values is finite, a sort of extension of Sard's theorem. And they also showed this fibration property, which is an extension of the work of Rabier, which is what allows this strategy using the generalized critical values. So essentially what you do is you compute the generalized critical values, which are the red dots on the bottom here. And then you choose sample points in between these values. And by testing the emptiness of the fibers at these points, you can decide what the infimum is. So the contents of the talk are firstly, mostly going to be covering this generalized critical value framework. So firstly, we'll look at the computation of the critical values and its extensions to other kinds of determinantal systems. And this will be joint work with Ellen Bostan, Hugo and my advisors. Then I'll introduce an algorithm we have designed for computing the set of asymptotic critical values. This is again with my advisors. Then I'll do a short note on the work I did on my secondment in Prima with Giorgio Ottaviani and Ettore Turati, a fellow Prima ESR who will be talking later this week. And then I'll just conclude with what questions my PhD answers and what are the further questions that you could ask. So starting with the critical values, we know by the Jacobian criterion that we can represent these algebraically by looking at all the maximal minors of the Jacobian matrix of a polynomial f and polynomials g1 to gm, defining an algebraic set. We add to these maximal minors, again, g1 to gm, as well as f minus c, where c is a new variable for the value of f. And if we assume that g1 to gm is a reduced regular sequence defining a smooth algebraic set, then the critical values of f are just the projection of this variety of this ideal onto the value space. And we know by Bertini's algebraic version of Sard's theorem that this set is zero-dimensional. And moreover, we can use the algebraic geometry dictionary to convert this projection into an elimination. And so a fast method that's commonly used in practice is to first compute a Grosvenor basis of this ideal with respect to a fast ordering, so like a degree reverse lexicographic ordering, which I'll call DRL in this talk. And then to use a change of ordering algorithm to get a lexicographic Grosvenor basis of the same ideal, which gives you a polynomial representation of the set of critical values. So the complexity of this first DRL step is well known for determinantal systems. We want to know what about the change of ordering step. So since our ideal is zero-dimensional, we know that the quotient algebra is a finite dimensional vector space. And so multiplication by any element of the quotient algebra is a linear map and has an associated matrix. Using the matrices M1 to Mn for multiplication by x1 to xn in 1993, Forget, Gianni, and Lazar and Mora gave the FGLM algorithm, which does this change of ordering with complexity nd cubed, where d is the degree of the ideal, or equivalently the dimension of the quotient algebra. And I give it here for the degree of the in the critical point setting. But in the generic case, you actually only need this last multiplication matrix Mn. This is the shape lemma that Hugh spoke about just then. And in fact, this matrix is very highly structured. It has many sparse columns and many dense columns. And so to take advantage of this structure and this generic property, in 2011 and later published in 2017, Forget and Mu gave this algorithm sparse FGLM, which has complexity in the order of QD squared, the dominant term, where Q here is the number of dense columns of this multiplication matrix Mn. And so firstly, one of the things we did is, of course, we showed that this genericity property applies to generic critical points to the generic critical point setting. And then the second thing you want to do is to estimate what this number Q is, so that you can accurately compare between FGLM and sparse FGLM. And to do this, we look at the reduced DRL Grosvenor basis, which we assume is known. And we show that the number of leading monomials in that basis that involve xn is equal to this number of dense columns, and then we count this number. So that's our main result. In the case where the degree of the polynomials is 2, we get an exact formula for this number of dense columns, and otherwise we get an asymptotic formula as the number of variables tends to infinity. And using this formula, we get an approximation of the matrix density, which in turn gives us the complexity improvement of sparse FGLM over FGLM in the critical point setting, which we find to be in the order of 1 over d times n to the 3 over 2. We also can see that in practice, our asymptotic bound closely matches what the theoretical number of dense columns is. As you can see on the left, it's almost identical. And our approximation of the matrix density is also very close as you increase the number of variables. So just as a brief overview of the sort of techniques we use during this proof. As I said, we look at the reduced DRL Grosvenor basis, which we assume is known. and we prove a structure theorem that tells us that from this, we can construct the multiplication matrix Mn for free. Then we look at the Hilbert series to find the combinatorics of this matrix and hence find the number Q. Just as a reminder what the Hilbert series is, we just look at the algebra and its grading by total degree. And then the Hilbert series, each term is t to some power, and then the coefficient of that term is the dimension of that term in the grading. Just an example, the Hilbert series is very closely related to the monomial basis of the quotient algebra you get when you're looking at graded term orderings. So, for instance, the degree reverse lexicographic is a graded ordering. And so, if you look at this monomial basis on the left, which we call a staircase, you can see it contains the monomial 1, x1, x2, x1 squared, and so on. And by looking at the total degree of these monomials, you can see it relates to the coefficients of the Hilbert series. So we mostly build upon these two papers. Firstly, this one by Fourier, Saffield, and Spenlauer, which is based on a work of Conker and Herzog, where they give the Hilbert series in this critical point setting. And we also build upon the work of Moreno-Socias, particularly in this paper in 2003, where he gives this conjecture called the orderly filling up conjecture. And as we saw from that last example, clearly, if you know what the staircase looks like, you can easily find the Hilbert series. But the conjecture is that this is actually a one-to-one phenomenon, and so that knowing the Hilbert series is enough to reconstruct the staircase. But our results rely on a weaker conjecture, weaker in the sense that in 2010, Pardue showed that Moreno-Socias' conjecture implies Froberg's. And this particular variant of Froberg's conjecture that we want to use is essentially saying that we take our quotient algebra, and let's say we quotient by an additional linear form to some power. Then we can find the Hilbert series of this new quotient algebra by looking at 1 minus t to the e times the old Hilbert series and truncating at the first non-positive coefficient. So if we just look at our past example, let's say we add to the ideal x2 squared, so we're quotienting by this x2 squared. Then we can find the Hilbert series of the new algebra by multiplying h by 1 minus t squared, and multiplying out and then truncating at the first non-positive coefficient, and you can see that the two things line up. So by putting all these combinatorial ingredients together, we can get our main theorem. But then we also have extended all of these techniques beyond the critical point setting to more general determinantal systems. So for instance, we could look at a matrix with with generic polynomial entries, so an L by M matrix, and we can look at the minors of any size. This is applications in cryptography, for instance, a generalized min-rank problem. We note that for this case, there's no simple form of the Hilbert series, well, that's known. And so we can't apply the full breadth of our techniques. But for this class of determinantal systems, so those coming from a symmetric matrix, now we have an L by L matrix with this symmetric structure. This has applications again in, of course, polynomial optimization. These kind of matrices appear in semi-definite programming, but we also have an application in quantifier elimination. And so our main result is an asymptotic number of dense columns for this class of systems. But we note that here, because we're looking at minors of any size, in order to end up with a zero-dimensional system, we need to prescribe the correct number of variables. And so here instead, we're looking at the degree tending to infinity. And we can see that the improvement of sparse FGLM over that of FGLM is at least in the order of 1 over MB. But the reason we're looking at this in particular is because for these certain sizes of minors, so when the size is L minus 1, L minus 2, or if you're looking at the 2 by 2 minors, then actually simple forms of the Hilbert series are known in these special cases. And so we can give dedicated estimates for the number of dense columns. In fact, the first one is is an exact formula. And for all three of the cases, we can see that the matrix density is well approximated. So in conclusion, we have derived the structure of the JRL staircase for generic determinantal systems, and this applies for critical point systems, more general determinantal systems, and in particular, those with a symmetric structure. We have derived an asymptotic formula for the number of dense columns in these cases, which are the fundamental parameter in the change of ordering step. And to see what I mean by this, it's sort of, the result is sort of future-proof in that we can use it to compare, say, more recent algorithms that rely on this kind of structure, FGLM-like algorithms. So we can compare these two algorithms, the first by Nagier and Schost, and the second paper this year by Bertemu, Nagier, and Safiel-Din. The complexities are in the order of d to the omega and q to the omega minus 1 times d, where omega is the exponent of matrix multiplication. We can again use our results to compare between these two algorithms and see what the complexity improvement is of the second algorithm compared to the first. So that concludes the bit about determinantal systems, and I'll now describe our contributions towards the asymptotic critical value computation. And essentially what it is that we have an efficient new algorithm for computing the set of asymptotic critical values under the assumption that the same assumptions we saw earlier, we have a smooth variety and defined by a reduced regular sequence. And we also have this third condition you see in the top right in blue, these are all satisfied for generic input. Along with our algorithm, we have a new degree bound for the set of asymptotic critical values. And to put this into some context, we can compare this to the bounds and the degrees of the critical values by Nien-Rensted, and the previously best known bound on the generalized critical values by Portico and Ionek. And to compare these three bounds, what you would do is you add the bound on the critical values to our bound on the asymptotic critical values and compare that to the bound on the generalized critical values. So we can see that we get this asymptotic improvement here. So our bound is a significant improvement outside of some small systems, in particular outside of the global case, which you'll see a bit later. We also give the first complexity analysis of an algorithm accomplishing this goal. And essentially we say that a finite superset can be computed in singly exponential time, well, singly exponential in the dimension of the ambient space. And this is particularly important because it means now the computation of the asymptotic critical values is no longer the bottleneck of the generalized critical value framework. So now all of the steps can be computed in, or can be done in singly exponential time. So computing critical values, the asymptotic critical values, computing the sample points and testing the emptiness of the fibers are now all singly exponential. So to get into the details of the algorithm, I'll just begin with a definition of what these asymptotic critical values are. So as we saw, they're analogous to the second element of randomization is to do with this differential condition. As I mentioned before, we introduced these new variables u1 to un, but we can see that this is kind of sort of redundant because we're going to set them all to 0 anyway in a second. And so to take advantage of this, we want to intersect the generic plane E, defined by these equations. And we can see it makes no difference at this point since E contains the variety on the left. But we prove a geometric result that tells us that we can replace these UIs with these AIE1 plus BIE2. And so we reduce the dimension of the sets we consider by n-2, and also significantly reduce the number of variables we work with. And this is what allows us to get the singly exponential complexity. Moreover, we have generalized this algorithm to handle polynomial mappings. So we can not only look at polynomials, but also maps going to C to the P for any P. We test our degree bound in practice. So here we have the previous, what we saw before, the bound on the critical values and the generalized critical values on the right by Rensted and Podka and Unick. And we compare it to our bound on the asymptotic critical values. So we have what we call the estimate. This is the degree of bound I showed you on the slide before. And the practice column is the degree that we reach in the algorithm in practice. And we test this for a variety of systems. And we note that for most of the case, our bound is an improvement. As I mentioned before, the first set of the examples, these ones. This is just an extension of the example I showed at the start of the talk. So this is a global problem, and so our bound isn't as good. And also we are not as good for systems with small parameters, but in the asymptotic setting, our bound is a significant improvement. On the timing side, we compare what we call the base algorithm. This is when we're not doing this slice of or this intersection of a generic plane. And we compare that to when we do that intersection. And we can see that in all cases, our algorithm is significantly faster and can tackle problems that were previously out of reach. And we also compare between doing this generic linear change of coordinates and not doing it. The reason for this is that, of course, if you do a generic linear change of coordinates, even though you only have to compute one set, you completely destroy any structure that the problem has, and so it can actually make it take a lot longer. And that's what we see for many examples. But yeah, in either case, the improved algorithm is significantly faster. So in conclusion, we have designed a new and efficient algorithm for computing the set of asymptotic critical values, which has applications for polynomial optimization and other problems in real algebraic geometry. We have improved the degree bound outside of the settings I showed you just then. And we've given the first complexity analysis, which, as I mentioned, is now singly exponential. That concludes the part of the talk on the generalized critical value method. And I'll just now have a brief exploration of some of the work we did in my comment on these two varieties of simple squares. So this first variety here, we call SOSK. This is just the variety of all polynomials that can be written as a sum of at most k squares with a fixed degree and number of variables. I know also we're in the homogeneous setting. The second variety, SOSKF, this is a bit more nuanced to it. This is when we're choosing a polynomial f that can be written as a sum of k squares. So it depends on the polynomial we choose. And the variety contains all the possible decompositions that that polynomial has. So just to tie this back into what we saw earlier in the talk, if we look at a polynomial f in this SOSK that is a sum of at most k squares, then we could look at the gram matrix of this polynomial f, which is the matrix that allows it to be expressed by what we see here, the bold x transpose times w times x. We can see an example below. So here the gram matrix is this matrix, or a gram matrix is this matrix here. And if this is a sum of at most k squares, then the rank of this matrix is at most k. And so what we really have is a close connection to the symmetric determinantal ideals we saw before, because we have a symmetric matrix with this rank condition. And indeed, if it is a sum of squares, then we can split this, we can decompose this W into some matrix A, so A transpose times A, which gives us the sum of the squares decomposition. So this matrix A is just coming from the decomposition you see on the left. And we note that there is a relation with the group of orthogonal matrices. So if you take any orthogonal matrix, so O transpose O is just the identity, you can plug it into the middle of this A transposed A, and you get a new decomposition, which is given by OAX. So for instance, if we just take the orthogonal matrix that just swaps the rows or the columns, then we get like this, and we get a new decomposition of our polynomial, which is just trivially swapping the order of the sum. So this shows we have an action of the orthogonal matrices onto the variety SOSKF. And in fact, our result is that this actually leads to an isomorphism in the case where we have at most two squares a generic polynomial. And this is particularly surprising because we know this doesn't depend on the degree of the polynomial. So even if you have a moment structure in the Gram matrix, that it seems to not matter. It doesn't matter. We also give the degrees of the varieties SOS1 and SOS2. So this is the variety of squares and of sums of two squares. And we also conjecture that the first result here, the one on SOSKF, actually goes much further. So we think that if you take some generic polynomial with fewer squares and you have variables, then this isomorphism still happens.
So all of this is over C, right? I mean, these are not really sums. I mean, I guess the over C sums really become, you don't care about positive semi-definite.
Yeah.
So nothing like this exists anymore. Right?
Yeah, so yeah, it's an important point to note. We're not talking about the real case here. We are just talking about the complex here. Because we just want to look at this algebraic set SOSKF, where you say treat the coefficients of your decomposition as variables, and then you just have that equality. You have these equalities within the coefficients to give you the variety. That's what this SOSKF is. So it's a complex object.
So it's in some sense some sort of uniqueness of the group action, right? That's what you were conjecturing, right? But this really needs to, I mean, you need a genericity condition, right?
Yeah, you do need to pick this F generic. So we pick the polynomial in, so it's a generic sum of most k squares. Well, because it's generic, it is a sum of k squares. Yeah.
Do you know the dimensions are the same?
That's our result. So yes, we have the dimensions are the same. So in fact, when we have this k less than or equal to n, we can decompose the variety into the action by OK. So we have finitely many different orbits. And yeah, in the case of most two squares, the case we just have one square, it's trivial. There is only one orbit, and we think that in fact it's the same for any k.
I see, but I told you k is less than or equal to n is how, because in principle you can have many more squares than than n. Even I mean, I guess what you're doing is you're taking secants to the variety, secant varieties to the variety of squares, right? And it should take longer than n to fill up the whole space, right? But I guess my question is, what happens if k is a little bit above n? Is it already automatically going to fail, or is it possible to extend this?
Yeah, so it all instantly fails. So
Even
if you take So again, we're in a homogeneous case. So if you take the number of variables to be the same as the number of squares, then the generic polynomial fails already. And it can fail quite dramatically. Okay. We no longer have this decomposition at all into OK. The dimensions are no longer the same.
Okay, so the dimensions stay in the field.
Yeah.
What you said about components?
So we can decompose the variety into the orbits. So we have some representations and some of the squares decomposition. You can look at the orbit of this decomposition by OK. And so as soon as you go beyond, as soon as you get to sort of the number of squares is equal to the number of variables, this is no longer enough to describe the whole thing. You have this difference in dimension.
Your normal form for this solution.
You mean like a sort of,
Open of the two.
I guess it's the catalectic probably would be, so you get the
For each one.
for each orbit, yeah, I guess. So now just conclude. So yes, so we've derived asymptotic formula for the fundamental parameter in the change of ordering step. And this has also been generalized beyond just critical points. So you can look at more general determinantal systems. So this is for applications in cryptography, polynomial optimization, and beyond. We've designed an efficient algorithm for computing the set of asymptotic critical values, and have brought the whole framework of the generalized critical value method for handling polynomial optimization exactly in the non-compact case to be a singly exponential problem. And we have also proved new and interesting degree and dimension results on these SOS decomposition varieties. So of course, the primary goal would be generalize everything I've said in this talk to include inequalities. We would also like to investigate this conjecture further. So this could have some connection with looking at moment matrices, because the particularly surprising thing about this is, of course, if you have just if you're just looking at polynomials of degree 2, it's quite easy. But as soon as you introduce this moment structure, it becomes you have this relationship between the coefficients in the matrix, and it becomes more complicated. And this could be connected to what we want to do next for the change of ordering step, as these moment matrices appear in many different applications in polynomial optimization and beyond. And so it'd be nice to know, how does this moment structure affect the change of ordering step? Can we take advantage of this, and how does this change the structure of this multiplication matrix MN? And we'd also like to design new, more efficient algorithms using maybe a different geometric characterization of the asymptotic critical values, because at the moment we have a gap between what we see in practice and the degree bound that we get as our theorem. And so ideally we'd want to close this gap, and this could maybe be done using different geometric characterizations, such as those based on polar varieties or by homogenizations and such. And it would also perhaps be interesting to look at so what are called non-trivial asymptotic critical values, which are those that are not found along the critical locus. Thank you.
Thank you, Anu. Are there any questions?
In the chat. So. Oh, I can't see the...
Any question?
So maybe I can, it's not a question, but more like a comment or suggestions. I mean, maybe, instead of just looking at the sum of squares with like a full monomial support, right? We could also investigate what happens when you limit your monomial support. So meaning that, you look at sum of squares or monomial. So your polynomials have monomial support coming from some polytope P. So, full monomial support will be some triangle or simplex, right? But and then you can still ask what happens in that case. So does that make sense? So you were going to take some of those squares, but your squares have limited monomial support. And then maybe I'm wondering if the same kind of results will apply, and maybe that has something to do with the dimension of your variety or something like this.
Yeah. At least in so of course we have some examples, some counterexamples to the theorem when it's not satisfied, so when the genericity is not satisfied. And so some of these don't have this full full support. And so yeah, it would be interesting to see what happens in the generic case in those settings. Thank you for suggesting.
Would it be enough with this conjecture for one polynomial?
So it was, I think we've looked at this, looking to reducing it to the case of just having sort of Z1 to the D, Z N to the D, whatever. And reducing it to just to that case. So I think yes.
Yeah, a semi-continuity.
Yeah. Yeah.
Maybe I have a question on your first topic about critical value computation. No, you did the general case, very nice. Then you, in a remark, you said I did also the symmetric case. And what's about the skew symmetric? Did you try?
I haven't tried that, but yeah, there are some. I think the Hilbert series are known, and this I can't remember how you pronounce it. It's like the fractions or the yeah. So I've seen some papers in this, but I haven't looked into detail about this. But I think as long as you know the Hilbert series, all the results you can apply them.
I'm not sure. Maybe there are additional difficulties.
I'm not sure. Yeah, it really just depends whether or not firstly if the variant of Frobert's conjecture is satisfied, whether or not we can have a variant of it in that case, and also one thing we need is what's called the unimodality of the Hilbert theory, and so whether or not that is satisfied, yeah, I don't know.
The first part, so you present you analyze the complexity for the critical points on, so assuming you are optimizing on a variety defined by the equation.
Yeah.
Could you apply this also to, say, the general problem of optimization where you have inequalities?
I'm not sure at the moment.
For instance, using so we have these KKT conditions, which are like the ones you consider, in fact, for different solutions.
Yeah, so you could look at say the power set of the inequalities, right, and then see which ones are satisfied. Look at all the different combinations. I guess you probably could. I haven't looked into doing this. So it doesn't seem like a very nice way of doing it. It seems like you have to do a lot of different things, a lot of different.
I mean, the minimizer, if you assume regularity conditions, the minimizers, they are in this KKT variety, so it's a union of critical points. So in principle, you could do.
Yeah, I guess. I'm not sure how it would affect things because if you're just taking the union, I guess if you're just doing this procedure many times, I guess you can just sum up complexity. But otherwise, if you want to look at a more dedicated, do it all in one go, then I don't think the Hilbert series would be the same. I don't know.
So let's thank you,